So I'm going to talk about a little bit about Inspire, and I'm going to also talk about our latest technology, which is really quite revolutionary. That's why we call it Simulation Revolution. So just getting started here, Altair, if you don't know, we have a long history in engineering services and developing really advanced solver technologies. We address problem statements that go from, down from electronics all the way up to structures at the subsystem level, all the way up to systems of products. So our engineering products and our services kind of address the full scope of the engineering and design process. And for us, we develop a lot of physics simulation codes, and we need to integrate those all together. So you'll see a lot of our products do these kind of multi-physics simulations, and we bring those in more and more into the design realm each year. We have a lot of physics that we develop through Altair, and if you look at the whole history of all the kinds of physics that are out, there's been probably more developed in the last few years even than in the probably 10 or more years before those. So it's just an accelerating field. And not only are we developing new kinds of physics, but the way we utilize those is changing quite a bit. So we have a full spectrum of things going from structures to system simulation and fluids and thermal and electromagnetic. So we know solvers. We really know solving technology and simulation, how to apply it in real-world conditions to get good answers. And we've been applying that more and more into the design process over the last 10 years or so. If you kind of look at the role of simulation in the design process as we go forward in time, it's growing more and more. You saw it through all the presentations this morning. They were almost more about simulation to some degree than they were about the design process and how simulation is driving the process more and more. So I guess don't need to say much more about that point because it's pretty established. But oftentimes the design process doesn't start with 3D CAD, so I do want to point out that many times it starts really with the schematics. What is the logic behind an entire design, especially a design that has control systems, which is many designs today, moving systems, systems that have any kind of energy moving through them in any kind of form, whether it's electrical or mechanical. And so that's usually the conceptual start point of a complex design. Then it kind of works its way into the 3D world where you get 3D physics that you simulate and you do your 3D geometry creation and optimization and so forth. And more than ever, the manufacturing is a big part of understanding how a design should be. The process you choose is going to influence the design of the part. You can optimize for performance, you can optimize for manufacturability, or you can optimize for a combination of the two, which is really the problem you're trying to solve day to day, not one or the other actually. So you heard Inspire mentioned, I think, 3 or 4 times this morning in one way or another. I felt a little picked on, but that's okay because I think it just underscores the importance of using optimization and generative technologies and things like that in the design process today. So Inspire for us used to be, in the very early days, a topology optimization product. It captured the great topology optimization capabilities of OptiStruct, which today are still by far the leading optimization solution. And they put it in the hands of the designers. And we've broadened that platform, so not only does it do simulation and optimization, but it has motion solutions in addition to structures. It has a whole suite of manufacturing simulation built into it now for metal forming, casting, molding, extrusion, things of that nature. And coming out later this year is a studio surface modeling system, which is that evolution of our previous product, which was called Evolve, which is being integrated more into the Inspire platform to do advanced surfacing as well and rendering. So just a quick example of how you use those technologies in the design process in the context of robot. So here, a robot, obviously like a car, there's a lot of control systems built into it. And usually the start point for a design of something like that is really modeling in a schematic way using a product. In this case, our product is Activate, where you create a working schematic diagram of all the logic which controls it. You can represent the logical components in the system. You can also represent all the physical components. And there's a very popular language, Modelica, which is used for modeling physical components like springs and dampers and resistors and circuit components and so forth. We can mix those all together in the same environment and get a working model schematic before you even begin a 3D design. You may start there, you may not. You may start in a 3D world. But if you have got schematics, if you've done that kind of system, we can use that to drive the 3D model. And that's an important step in the design process because the way things move really influences a lot about their structure. Things aren't static, and dynamic loads tend to be quite high. They vibrate. and you really want to design for the vibrations and the dynamic loads of things as well. So here we put the motion solution together for this 3D arm that we're designing. You can see it's got some blocky members there. Before we've done any of the optimization or generative design or whatever you want to call that inside of those components, we're actually running it through all of its real-world paces. Okay, and then those loads from all the motion simulation that you've driven by the motors now get immediately put into those parts for doing their topology optimization. The number one thing people always do wrong when they start to use all these technologies for optimization is they try to do individual parts separately, they try and get all the boundary conditions right, figure out all the load cases. So having a situation where you're trying to figure all that out, that's where all the mistakes get made first and foremost. So being able to generate the load cases from real-world scenarios is really important to the process. It also exposes the optimizer to all the different conditions that part's going to see, not one load case. You know, we see the emergence now of these kind of interactive controls where you move the geometry and watch the stresses change. That's good. That gives you some insight into how the design works. But really, eventually you're just chasing stresses around by moving here and moving there, changing the stress there, chasing it around. How many load cases are you looking at simultaneously when you do that? You're making one load case worse when you adjust for another. So it's not really the way the full design process needs to work. You really need to use process that has optimization built into it. So in this case here, we've done the optimization, and now we've redrawn the part using our PolyNURBS technology, which gives you this smooth B rep, but it's also like a sub D as well, so it gives you a nice control structure, which is great if you want to do further downstream redesign of that part. At the same time, we can generate an automatic B rep for you as well, which I'll show you in just a second. But now once you have a part designed, then you want to go through the manufacturing simulation steps. So a little bit later this year, we're releasing our 3D printing simulation for metals. So it'll actually let you take your parts from the assembly, put them onto a bed, put in your supports, modify things. Nice thing here is that it's all part of that same Inspire model. So once you put your supports, do the print simulation, you don't like it, something's not good, go back, you can do some re-optimization or change the design of it so you can keep going right within the same product. Same for all the other manufacturing methods I talked about. So we have a very nice casting solution here. And not only lets you simulate the casting, but now you can go back and optimize the placement of things like risers and runners and diameters and positions. So you actually can optimize the casting process as well. And so those are all kind of the capabilities that we have in that Inspire platform today for doing that sort of simulation-driven design. One new feature coming out, because it's probably the most requested, and we got a little behind on this, but we caught up, which is the ability to generate the B-reps right off of those results. So smooth results coming out of Inspire right out of the can. So you can have facets if you want them, you can have PolyNURBS if you want them, or you can have a NURB surface that's all smooth as well. So happy to release that in a few more weeks here. Okay, now on to SIMSOLID, which is almost too good to believe in many ways. But you know, Altair's got a lot of people in simulation, as I mentioned. We have hundreds and hundreds of PhDs working on physics simulation. And when we first saw the technology, like everybody else, we were incredibly skeptical. But it is for real. And let me tell you a little bit about it. So where it plays is, you've seen a lot of examples of doing parts, right? You can simulate a part with FE, no problem. You mesh it, and it's not that big a deal. What we've done here, though, is what if you have a CAD model, which is a really big assembly? Okay, that's really tough. You can't model every nut and bolt and screw, every single part. There's some 7,000 parts in that structure right there. Setting that up in any form of FE is a big task. You know, getting the mesh, there's lots of thin parts, there's a lot of contacting surfaces and fasteners. To set that model up in any system today is a lot of work. Days and days probably work to get it all right before you can trust it and run it and validate it. With SIMSOLID, it attacks the problem straight on. So yeah, we have 7,700 parts in that thing. Lots of nuts and bolts and things as well. You literally, with SIMSOLID, we've reformulated the approach. It doesn't use traditional meshes at all. It still uses some of the fundamental theory and the very origins of finite element theory, but we don't discretize with all these nodes across the field and put 6 degrees of freedom on every node. Instead, it formulates higher order mathematics through those surfaces. And so entire parts become like FE models in and of themselves, or FE elements. So it can solve the problem with very little memory and extremely fast. And it can do it very accurately, and it can manage all the context and details. There is no other software in the world that can do this. It is truly a breakthrough. So if you look at that particular model, you can see it's run that assembly of 7,000 parts or so. It did it in about 1 hour of setup, including bringing in all of the model and everything from CAD. You don't touch the CAD. You just literally bring in the CAD. And it can have some gaps in it, no problem. It can have overlaps. Doesn't cause a problem with it. And it'll find all the contacts and set them up for you. Yes, you can review it and so forth. But generally, you don't touch much of the model. And then it runs the whole simulation in this case, 30 minutes for the first time through. It's not interactive speed, but if you were going to do that model with any other traditional accurate method, it's going to be days of work to set that up. Okay, so let's see it applied to some other areas here too. So it's been used, it's relatively recent, it's only been on the market for less than 2 years now. And came to Altair in fall of last year. And we've been taking it to our customers. And it's a fun sales cycle with that product, because you take it, they try it, and it's amazing. It just works on their products. I want to point out some of the importance. So we saw earlier you could create assemblies really quickly in some of the CAD systems today. But they're welding assemblies together. They're making voxel meshes across boundaries of parts, and then they're trying to put in pseudo contacts. We don't do anything like that. That is not how you make a proper assembly model. Real assembly, there's contacts, there's pre-tensioning and bolts. There's contacts where they lift off from one another and they deform the contacts. All that stuff is really important to an assembly model. That's where all business takes place. So those interfaces, those assemblies, are very important to model correctly. And that's a big difference from just voxelizing through those things like they don't exist. So it's really good at doing the small parts. If it's even a moderate-sized part, it's going to blast through that thing in a few seconds, just literally just a few seconds. So some of these times I'm showing you are for very big assemblies. So the sweet spot here is if you look at classic FEM, the bigger your model, it just almost goes nonlinear because there's so many details you have to take care of. It loves big models in SimSolid. It's pretty much a linear process. Bring it in, set it up, run it really fast. It also has a lot of physics, and there will be more coming as well. So just if you look down the left column there, so there's standard statics, modal, nonlinear geometries. We got frequency response and thermal already, random response. So it's already a pretty complete set of physics. But that will grow. Handles many material types. Look at the connections, so it's got all the kind of connections in addition to spot welds and seam welds and bonded and sliding and lifting contacts and all that kind of thing. We've added rivets for the aerospace industry, very common to use rivets, and more in the auto industry as well. And bushings, so we got it handled really. Now, just looking at a few applications of the technology in the automotive world, it's starting to catch on. And this is going up against the big traditional FE codes where they spend a lot of time. True story, I have a brother that works in the auto industry in Detroit, a couple years older than me. He's a design manager for chassis. And last year I got a call from him. I was actually having dinner with him, I was alive. He said, have you heard of this thing, SimSolid? And I couldn't tell him, but we had heard of it. At the time, we were just about to seal the deal. And he says, I'm not kidding you. I had this change to a frame that looked a lot like this. And I took it down to the FE department, and I said, can you guys make a change? I have to change one of the rails and change the bracketing around it. And his FE guys were down there, it's like, yep, I'll get you about 3-4 days. And he had a SimSolid evaluation going on. The guy in the same conversation said, I'll do it. And he got answers that afternoon. And my brother's like, I've never seen anything like it. And it was amazing. So a few days later, I was able to send him a mail and let him know that, yes, we had heard of it and we were using it. So, okay. General machinery, again, big, large assemblies, lots of contacts, dynamic problems. Works great. So we're seeing hundreds of parts quite often, these assemblies. Total setup time, runtime, half a minute. Just more examples here for Andron. I think I saw them featured in one of the sheets here today. Lots of contacts, lots of moving parts in there. Wing assemblies. So we're not talking about just small models here. This is sheet metal in aerospace industry is complex. Lots of rivets and joints and box sections and so forth. So these assemblies are are quite tricky quite often. They don't even do a lot of finite element normally in the aerospace world. They use other methods that are more approximate, or they use formulas and so forth. So we're seeing a growth in these directions as well, because this makes it really possible. Architecture is another great one. You get a lot of these big assemblies with lots of contacts and so forth. Thousands of beams connected together. We're talking about on the left there, 2 minutes for a solve, less than a minute for the other one. These are first solves. Subsequent solves are usually about a third or a quarter as long to run. Because once it's set up its equations, it just resolves them again. So these are real-world companies. It also is particularly good at doing these types of organic problems as well. So when you get MRI scans, what's cool about SimSolid is it can work from CAD geometry, the NURBS data, but it can also work from faceted information as well. So it can formulate its equations through that type of data. So bone structure is great. Detailed lattice structures, perfect. Lots of detail, no problem. So just a little bit of how does it work in the workflow. We've seen the Brompton bike. We saw the keynote this morning. Very cool. So those guys have been working more and more with Altair. So here we just brought that in from a SolidWorks model. In this case, if you happen to be working on desktop using SolidWorks, no problem. We have great integrations with SimSolid between SolidWorks, but also, as you saw, with Onshape. We have a cloud version, and we love to see it working with Onshape. We really believe strongly in the cloud model as well, and there's been a lot of investment in this product to make it available through cloud too. And I think it's a great combination. So the workflows are pretty traditional. You know, you just bring it in. There's no meshing step or anything like that, no cleanup steps. You don't have to think about the geometry. You can just immediately start putting your loads, forces, constraints, and so forth. What's cool is it finds contacts. It uses the same principles as Inspire. It's looking at the features of the geometry to detect where it knows there's contacts, and it suggests those to you. So you can either override those or accept them, so it gives you control over that. You hit the run button, and that's the Brompton bike, all the parts in it. I think it said there was 100 parts or something. I missed the number. But it's run the whole simulation. And the first time through is about 1.25 minutes to run that simulation. So on subsequent runs, though, since it's already got the equations, if you update a part or you're just changing the load cases, it's going to run in something like 1/4 of a minute, something like that. So down to 15, 16 seconds. The good part is it's accurate and you can trust it. These are real answers. These are not voxelized approximations with poor contacts. And that matters. You're going to get different answers every time if you don't model the contacts correctly. And I think then we're going to, I think we just imported a model out of Onshape in here. So we have the cloud version as well. It can just import individual parts. And you don't have to go very far, right? There we are in Onshape, just pulling a part out, update your model, rerun it. So you don't have to walk down the hall to use this. It's just the same guy sitting in front of his CAD system, updating his geometry live, using the live APIs that we have to Onshape in this case. And so it really blends quite seamlessly into your existing workflow. Okay, so that gives you a pretty good idea what it does, and it's pretty quick to learn because it's pretty traditional in how you set up loads and boundary conditions and so forth. So one other thing we're doing with the technology, we're also adding it into the Inspire product. So we'll have a combination of all that topology optimization and the manufacturing and super fast, high accuracy simulation built into that product as well, which we're pretty excited about. So that's it. That's all I really wanted to talk about today, to introduce you to it. It's easy to get hold of if you want to try it. There are some theory papers on it, but it is it's something you just have to try to understand what it can really do. So we're quite excited. Again, sweet spot is really any form of linear and transient type analysis that you saw on that list there for either individual parts or full assemblies. So please have a look at it, and I hope you can get a chance to use it soon. So thanks.